Today we're going to cover the second day of the fluid states. Our main objective would be to understand the origin of Pascal's and Archimedes' principles, as well as their applications, and then explain Bernoulli's principle and its application in producing lift. We'll cover this bell ringer first, and then I've got one thing that I forgot to cover in section 1, so we'll go back to that before these notes. So once you work on this, pause the video and we'll show the solution here in a second. We know that pressure is force over area. In this case, I want to figure out how much force is on a sheet of paper. So force is pressure times area. Well, we said that pressure due to air is about 1 times 10 to the 5th newtons per square meter. And if we take that times our area in square meters, we can get our pressure. Our area would be 0.5 meters times 0.8 meters. If we multiply all those together, we end up with 40,000 newtons of force. The next part says, what is this pressure in pounds? Well, if we modify this, all we have to do is change our pressure units from newtons per square meter to 14.7 pounds per square inch, but that means my area has to be in square inches. So let's first do that, convert our 0.5 meters and 0.8 meters to inches. We know there's 1 meter is 100 centimeters, and there are 2.54 centimeters in 1 inch. So taking 0.5 times 100 divided by 2.54 gives me 19.7 centimeters. And then doing the same thing with my 0.8 meters. 100 centimeters per meter. 1 inch is 2.54 centimeters. We end up getting 31.5 centimeters. Just kidding, those are inches in both cases. That was our goal, to change to inches. Now I can plug in my 19.7 inches, times 31.5 inches. Take that times my pressure of 14.7 pounds per square inch, and we end up with a force of 9,120 pounds of air on that small little piece of paper. So it doesn't seem like a lot, but there's quite a bit of pressure surrounding us continually. Now we need to go back to yesterday's stuff so I can finish up one section here. Swimming under pressure. We know that a fluid a pressure in a fluid is the same in all directions. This is kind of Pascal's principle. You apply a force or a pressure on a confined fluid, it's diminished throughout. Pressure in a fluid is the same in all directions. We also know that pressure is force over area. Well, weight is m times g, and that's really the force. I can replace my force with the mg. Density is mass over volume. Now this P stands for weight density, so we're going to use this as the weight density, or the density of our fluid in these systems. If I rearrange this density equation for mass, we get mass equaling density times volume. I can then substitute this in for my mass right there, and we end up getting pressure equals weight density times volume times G divided by A. Well, volume is area times height. So if I substitute this in for volume, we get pressure is weight density times area times height times G. And at this point, you'll notice the areas will cancel out, and we are left with pressure equaling weight density times height times G. G we know is acceleration due to gravity, which is 9.8 meters per second squared here on Earth. H is your height in meters, and this is your weight density, or fluid density, in kilograms per meter cubed. And that would give you pressure in pascals. Notice the units for this equation for density are kilograms per cubic meter. And also the interesting thing is the only variable in this equation is the height. So the pressure of water when you're swimming depends on the density of the fluid, which is a constant, G, which is a constant, and the depth. The deeper you go, the more pressure you're going to have on you. And that's what we should have finished from yesterday. We're going to use that in our discussion today as we continue on 13.2. So 13.2, let's get to buoyancy and Archimedes' principle. The buoyant force is an upward force exerted on an object by a fluid. Anytime you put something in a fluid, usually you think of sticking something in water, you weigh less. And the reason you weigh less is there's a force pushing you upward. And that's called the buoyant force. Now this is true in any fluid. Here's how this works. You've got this block of some substance underwater. H represents the distance from the top of the level of the water to the top of the block, and L is just the length of the side of a cube. We just derived that pressure is equal to weight density times height times G. And we know pressure is force over area. So I can figure out that the force is really your weight density times the height times G times A. So what is the force on the top of this block? Well, the force on the top would be weight density times H times G times A. What is the force on the bottom of the block? Well, that would be weight density times the height here is H plus L times G times A. If we take the force on the bottom minus the force on the top, and I'm going to expand this out for the force at the bottom to PHGA plus PLGA That's just the force of the bottom. Now I have to subtract this, which is the force on the top, weight density HGA. What you'll notice is these cancel out. So what we get is the net force, the difference between those two forces is weight density times L times G times A. And L times A, length times the area, is volume. So the net force, which turns out to be our buoyant force, is equal to weight density times V times G. That is something you want to put on your equation card. If you want to calculate how much force is pushing up on a submerged object, all you have to do is multiply the weight density of the fluid times the volume times G. So notice it really depends on density times volume is mass, m times g is weight. Your buoyant force is really the weight of the fluid that's displaced by that submerged liquid. Here's what Archimedes' principle says. An object immersed in a fluid has an upward force on it equal to the weight of the fluid displaced by the object. And we can come up with that directly from this equation. Density, we know, is mass over volume. Take that times volume times g, we're left with m times g, which we know is weight. So the upward force, your buoyant force right here, is equal to the weight of the fluid displaced by the object. A couple things it's not equal to that sometimes students get messed up on. It does not depend on the weight of the object. If I stick a 2-gram object in water and I stick a 50-gram object in the water, if they have the same volume, they're going to have the same buoyant force. Because both of them have the same volume, they're going to displace the same amount of liquid. So it's the weight of the fluid displaced, not the weight on the object. And the difference between an object's weight and its buoyant force will determine whether or not it will sink or float. If the buoyant force is greater than the weight, you've got a greater upward force, so the object is going to float. If the buoyant force is less than the weight, then the downward force of the weight will pull it down and it's going to sink. So anything that floats has a buoyant force greater than the weight of the object. All objects in a liquid, whether they sink or float, have an apparent weight that's less than its actual weight, because everything in a fluid does have this buoyant force acting on them. To figure out your apparent weight, you just take the actual weight minus your buoyant force. If we drew an object in a fluid, this would be the force due to gravity, or its weight. This would be the buoyant force going up, is apparent weight, would equal this minus that. These have to be in equilibrium. So if the thing weighed 25 newtons and the buoyant force was 20 newtons, you have an upward force of 20. This normally weighs 25 in air. It would appear to weigh only 5 newtons in that fluid. So things will weigh less submerged. Last thing we want to talk about here is fluids in motion, and this leads us to our third and final principle, which is Bernoulli's principle. Bernoulli's principle says as the velocity of a fluid increases, the pressure exerted by that fluid will decrease. As the velocity of a fluid increases, the pressure exerted by that fluid decreases. And some examples of how this is actually used would be in the case of airplanes and spoilers on cars. And I'll show you what we mean here in a second. Just for the record, this does not apply to turbulence. If I've got airflow that's going straight through a pipe or through something else, that would be streamlined. If you have airflow that's going this way and this way and this way and this way and this way, that would be turbulent. And again, this principle doesn't apply to turbulence, so we're talking about a nice streamlined flow of air. Here's how this kind of works. You can imagine this is a side view of an airplane wing. If wind is coming from the left or the front side of this wing, it has to get to the back side at the same time. Well, the distance for the air to travel on this side compared to this side, it has to go further on the top than the bottom. Well, in order to go further, it has to be traveling faster. And we know that if you increase the speed, it decreases the pressure. That's what Bernoulli's principle says. So I've got the wind traveling faster on the top, which means I have low pressure regions on the top of the wing and higher pressure regions below the wing. That high pressure acts like a little force pushing this wing up. And as that airplane goes down the runway, the faster it goes, the greater the difference in pressures, and eventually you can get some lift and cause the airplane to fly. The other example we said were spoilers. Well, what's the point of a spoiler? A spoiler on a car is really kind of like a wing, except upside down. So now you have high pressure on the top and low pressure on the bottom. So it's going to add extra pressure to push the tires down so they get better grip on the road. We've got some great examples and demonstrations we're going to show you in class dealing with Bernoulli's principle. Hopefully you'll be able to figure them out before you see them. You've seen this lecture.